Hello everybody, I hope you're doing well. Welcome back to another video reviewing your probability and statistics fundamentals. So in this playlist, we're going to be continuing our discussion on least squares. So we're not really touching on actual probability, we're kind of touching more on regression analysis. So in this video, we're going to be talking about a concept called the R-squared coefficient. Now I know that in some of your past classes, you might have seen this word R-squared coefficient and wondered, what is this mysterious term doing, right? What does this actually mean? We might know how to calculate it, but explaining what it means intuitively, that's where this video comes in. So as you may recall from the previous video, we have derived a formula for finding the optimal slope and y-intercept to fit our line, right? So just to motivate our discussion of the problem, we have some data, right? So we have some data points here, and we want to find which is the line that best fits this data, right? And captures the overall trend, right? So maybe this red line. We want to find what is the equation of this red line. And we know that a line has a slope and a y-intercept. So if we can solve directly for the optimal value of the slope and y-intercept given your data set through these two equations right here that we have derived in the previous video, then we'll be able to find the line of best fit and make meaning out of how good this fit is. So in this video, we're going to use the R-squared coefficient as a way to understand how good did we do, right? How good was our line overall, right? So you might be wondering, well, don't we already have a metric to determine how good our line best fits our data? Well, yes, we do, right? It was this summation of squared distances we wanted to minimize, right? So if we had n data points, right, you want to minimize this summation, right? Y hat minus y sub I squared, right? Where if you have this data set, right, and you have this line of best fit, right? What we want to do is minimize the distance from this y value to the corresponding y value on the line. So we want to essentially minimize the sum of these squared vertical distances. And we talked about why we want to care about the squared vertical distances, right? Because if you're far from the line in any direction, above or below the line, we still want to penalize, right? And the squaring allows us to penalize large distances, right, between the data and the line of best fit. So we want to minimize the sum of these square distances, or these vertical distances, shown in green right here, right? So that's the metric we use to optimize to get the equation for the slope and y-intercept. But we're going to introduce another metric called the R-squared value, right? So R-squared is essentially another way of saying coefficient of determination. Now that phrase might sound a little daunting, right? And you might have seen it before, but rest assured, this video should shed some clarity, right? But before I proceed into what this coefficient of determination is, right, I just wanted to highlight something here. So this term, right, which is the sum of the squared vertical distances, right, we call this y hat minus yi as in this vertical distance shown in green. We call that a residual. So y hat minus y sub I is a fancy way of saying residual, right? So residual is basically y hat minus y sub I. So what we're doing here is minimizing the sum of squared residuals. Now to understand like the R-squared value, let's backtrack a little bit to fitting lines in the first place, right? So let's draw a little bit of a bigger picture, right? So I have some data here, 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 maybe here, maybe here, here's a value, right? Now, suppose that we didn't know about the equation to find the optimal slope and y-intercept of the line, right? What will you do in this case? Well, we can propose that maybe the best way to predict the y value is predict the average, right? Because intuitively, the average captures what's the overall value, right, of the y's, right, in our data set, right? Recall that our data set is of the form x sub 1, y sub 1, x sub 2, y sub 2, and you have n of these data points, right? So it might make sense that for given a new value of x, we might as well just predict the average, right? The average y value, right? So this blue line is going to capture that, right? So this is essentially y bar, right? And now let's take a look at what this vertical distance is. What is the sum of the squared residuals if this horizontal line, y equals y bar, happens to be the line that fits our data? Well, here's our squared distances, right? Okay, so I'm just drawing all these vertical distances from these data points up to y bar. And you'll notice that to write the expression for the residuals, right, all we have to do is take each data point, take y bar, subtract from the y value, and then square it, right? We want the sum of the squared residuals. So this sum of squared residuals will actually become the sum from I equals 1 to n, as we have n data points. And we're going to do essentially y bar minus y sub I squared. And just to flip the order a little bit, since we're squaring a number, so if you have a minus b squared, this is equivalent to doing this. So I'm just going to flip the order around a little bit to make it nice, but this reason is why I can flip the order, and the form is still equivalent. So this is equal to the summation from I equals 1 to n of y sub I minus y bar squared, right? So if we had this horizontal line, y equals y bar, and naively fit our data through this horizontal line, this is the sum of residuals you're going to get. This is kind of like our error from naive fitting, right? So you might ask, why are we fitting naively, right? Isn't a horizontal line not necessarily the line of best fit in most cases? Well, you might be right. So let's actually draw a better line of best fit, maybe a potential line of best fit. I'm going to draw this in red. So suppose this was a line of best fit that I got, where the slope and y-intercept come from these two equations right here. So now let's figure out what this error is, right? So let's figure out how well does this red line do in fitting our data. Well, we'll take the sum of square residuals again, right? I'm going to use black to draw the residuals. So from this data point, right, we take the difference between this y value and whatever y value the line predicts, right, for this corresponding x, right? And we do the same thing here, right? So we get the vertical distance from this data point's y value to the y value predicted by the line, and so on, right? So these are the vertical distances that we're going to take the square of and sum. And now we want to figure out what is the sum of these squared vertical distances shown in black, right? Well, now that we fit our so-called better line in red, the residual or sum of squared the sum of squared residuals, right? Residual is essentially the difference between, like, it's essentially the vertical distance, right? So this y value from the prediction minus the actual y value, right? So we want to take the sum of the square residuals now with using this red line as our prediction, right? Which seems like a better line of best fit. So the sum of square residuals is now going to become summation from I equals 1 to n, as we have n data points. And now we're going to take y hat minus y sub I squared. And what do we know about y hat? Well, y hat is essentially the value predicted by the line, and y sub I is the truth value of the y data, right? So what is this? This is going to represent how much error we get from fitting the optimal line to the data set. And recall that our data set is essentially x sub 1 comma y sub 1, x sub 2 comma y sub 2, so you have n of these ordered pairs, right? So this expression here, this second expression for the sum of square residuals is how much error do we get from fitting the optimal line, right? Or the optimal line of best fit. So you might think that, okay, if we have a horizontal line and the horizontal line is simply the mean value of the y's, and that's what we're predicting all the time, we might think that this error right here, shown boxed around in red, is probably going to be bigger than this error we get from fitting the optimal line. I guess like that kind of makes sense intuitively, right? So let's let this red box expression be E sub y bar, right? So this is essentially like the naive error, right? And let's let the screen box be the error from the optimal line of best fit. And I'm going to call this variable E sub B, right? B for better, right? So what we want to know is how much error did we decrease by, right? Well, what is the percentage decrease from the naive error to the better error, right? Well, we take the change, but we take the difference between the naive error and the better error and divide by the naive error, right? We want to figure out the percent change or the percent improvement. Well, so the percent improvement from using a naive line to fit our data to using the more optimal line is going to be this, right? The percent improvement is simply E of y bar minus E of B over E of y bar, right? This is like the percent change from the naive error to the better error, right? So this is almost like essentially our percent decrease, right? How much better did we do, right? And when I mean better, we want a greater reduction from E sub y bar to E sub B. So imagine that the naive error was 1,000,000, right? And then when we fit an optimal line, our error becomes 500. Well, we have had a huge decrease in error, and clearly the optimal line is fitting the data better. But how much did we improve by? How much uncertainty has been captured by this red line that wasn't captured by the naive blue line? That's this percent improvement we want to find, right? And we'll notice that this percentage improvement, we can expand the fraction out a little bit, right? So we have E of y bar over E of y bar minus E of B over E of y bar, right? So we'll notice that this term here goes to 1, and this term here stays as is. And since E of B is assumed to be less than or equal to E of y bar, basically this number is between 0 and 1, right? So 0 less than or equal to ratio less than or equal to 1. And this is equal to the R squared value. So let's wrap up and talk about the intuition behind this. So the R squared is telling us by fitting an optimal line to our data, how much uncertainty has been captured. So how predictive is our line essentially, right? And a line of best fit is more predictive on our data if we have a reduction from the naive error, right? Which is through just fitting the average, right? And making that like the value to predict all the time versus fitting the optimal line. How much better is our optimal line than the baseline of the naive error, right? So you can think about this blue line as kind of a baseline or a control, right? And the red line is kind of our optimal line of best fit. So how much better in terms of performance, or how well did this red line capture the overall trend in our data to figure out what's the percentage improvement, right? So in other words, how much better is this red line at fitting the data better than this naive blue line, which is our baseline? So the R squared tells us this, right? And what we want is the smaller that the error is in the better line, which is the red line, the better that the line of best fit captures the trends in our data, right? So imagine that we have this red line and it just somehow nicely captures the trend and it's really close to each of these data points, right? So these vertical distances shown in black are really small. Well, that red line is clearly capturing the trend in the data much better than the baseline of the blue line, right? So E of B will be much smaller than E of y bar, which is our baseline error. So thus, we have a high R squared, which means we have high predictive power within this line of best fit. So you can think about how good is the optimal line at capturing trends in the data. So that, my friends, is the intuition behind the R squared value. And you might see E sub B and E sub y bar denoted differently, right, in your textbook. But this is the general formula you want to use for R squared, right? And all you need to do to find the R squared is fit the naive line, which is the blue line, take the sum of the residuals between the y values of the data points and y bar, right? So that's what this red expression is. And then now fit the optimal line shown in red, and then basically evaluate this expression shown in the green box. And now that you have these two expressions, all you have to do is substitute into this formula, and you have calculated the R squared of your data. So just to give a brief example, suppose that R squared is 0.5. What does that mean? Well, it means that we have reduced the error, like in terms of our predictions, by 50% by choosing the optimal line to fit our data. So 50% of the uncertainty in our data in terms of the spread is captured by the line of best fit through this data. So you want R squared to be as close to 1 as possible, because then that would mean that our line nicely fits the data. And we've captured more of the uncertainty and more of the variance within the data, or more of the spread. So hopefully that kind of gives you some insight into what R squared is, and hopefully demystifies this idea to you. Till next time, we'll probably do an example of linear regression on a toy data set so that we can at least make this idea more concrete and see kind of what we're doing. But I hope to see you soon, and have a good rest of your evening.